We're looking at the motion homework problems, and this again is in your packet, and this is a continuation. This is the second night homework on motion. Beginning with problem number 24, which is in your packet, and the answers are there. So I may not do everything here, but I just want you to have time to review these problems. Problem 24, we have a particle that's moving on a number line that's shown in the figure. Part B shows the position of the particle as a function of time. So what we have in this graph is a position function. So make sure that you correctly, before you begin working, you identify the function so that you interpret it correctly. Alright, so we have a position function here which tells us where the particle is. Question A, when is P moving to the left and when is P moving to the right? Well, since this is a position function, whenever the function is decreasing, the particle is moving to the left, and whenever the function is increasing, the particle is moving to the right. And of course, when the particle is standing still, there's no change. Alright, so I'm going to highlight in blue the places where the particle is decreasing. So we can see clearly that when the particle is moving left, the graph is decreasing. And we can easily see that if this is measuring the position is moving to the left because the function is decreasing. I'm going to highlight in red the places where the particle is moving to the right, which means that the graph of the function would be increasing. And then I'm going to highlight in green the places where the particle is remaining constant. So for example, in that region, the particle remains at 2 centimeters the whole time. So that's pretty easy. But keeping in mind that that is a position function. Part B, they're asking me to graph the particle's velocity. So again, we're considering velocity or slopes of position. So we did this in a problem in the other video, except we had a velocity graph and we did acceleration. We're going to do the same thing. We're just basically going to find the slope of each segment. So for example, if you look back up at the position function at the first segment, which is highlighted in red, the slope there, we're going to rise 2 and run to the right 1. So the slope is 2, so the velocity is 2. So from 0 to 1, the velocity is 2. So you're simply going to graph a series of little horizontal line segments that indicates the slope. From 1 to 2, we can see that the slope is 0 because the particle is not moving. Velocity is not moving. That makes sense. From 2 to 3, we're going to drop 4 and run to the right 1. So we're dropping 4, right 1. So I need another increment here because that's negative 4. So from 2 to 3, negative 4. From 3 to 5, we have a slope of 0. And from 5 to 6, we have a negative slope. We're dropping 2, running right 1, so that would be negative 2. So 5 to 6 is negative 2. And those are your slopes. Now the next thing that it asks us to do is to graph the speed. So the only thing that I'm going to do for the speed graph, so what you see currently is the velocity graph. The speed graph would take these two segments that are negative. Remember, over and over and over again, speed is the absolute value of velocity. So it's simply going to take those two segments and flip them above the x-axis. So this segment that's at negative 4 would now go to positive 4, and that's from 2 to 3. And then this graph that's at negative 1.5 would flip to positive 1.5. like that. And then again, the speed graph would be everything that's x-axis and above. Okay? Problem number 25. This time they give us a velocity function. So again, identify the function first every time. Question A. When does the particle move forwards, backwards? Now we're interpreting velocity, so whenever velocity is positive, the particle moves forward. Whenever velocity is negative, the particle moves backwards. So I'm going to highlight in red when the particle is moving forward, velocity positive. So the velocity is positive here, velocity is positive here, velocity is positive here. I'm going to highlight in blue when the particle is moving backwards, velocity negative, velocity negative, velocity negative. So whenever the velocity is negative, the particle is moving to the left. Part B, when is the particle's acceleration positive? Well, acceleration, positive, negative, and zero. Acceleration, we're considering slopes of velocity. So since this is made up of a series of linear segments, I'm going to get rid of my highlighting on my graph because now I'm going to highlight slopes for you. So let's go with blue for positive slopes. So the slope is whoops, still got my eraser, got my clock. Slope is positive from here to here. Let's go red with negative slopes. Slope is negative from here to here, and from here to here. And let's go back with the green again for slope being 0. So in the red region, the acceleration is positive. Sorry, acceleration is negative. In the blue region, acceleration is positive. And in the green region, acceleration is 0. Question C, when does the particle reach its greatest speed? What is speed? Speed is the absolute value of velocity. So since this is a velocity graph, we are trying to determine the value that is the furthest away from the x-axis. It's a y value that is the furthest away from the x-axis. So it can be, our candidates, so far this looks like it's far away. So this has a chance of being the greatest speed, and this has a chance. So the question is, which of these two is greater? Well, there are no increments on the graph, but it clearly looks to me that this value is further away than this value up here. So the greatest speed occurs from 2 to 3. Letter D, when does the particle stand still for more, let me move this out of the way, when does the particle stand still for more than an instant? Okay, well, if you look at the graph, we'll get rid of this again. If the particle is standing still, that is the velocity. Velocity is 0. And the only places that the velocity is 0 is at 1, 5, and 7. So there's no period of time that the velocity stands still for more than an instant. Next question, we have another graph of a velocity function. Notice that every time I do this, I write down what graph I'm looking at because I want you to do this on your quiz. When does the particle reverse direction? So again, that means v of t changes sign. And the velocity changes sign at 1 second. The velocity goes from positive to negative. And at 4, we'll call it 4.2 is an approximation. At about 4.2, the velocity changes from negative to positive. So the particle is changing, reversing directions. Part B, when is the particle moving at a constant speed? The only place that I see a constant speed is in this little region right here. So that would be from 5 to 6. When is the particle at its greatest speed? Speed, absolute value of velocity. So again, I am looking for the place on the graph that is the furthest away from the x-axis. So the candidates are, that looks like it could be the furthest away, or possibly up here. So now let's compare those values. That's -3 approximately, and this is about 2. So the greatest speed is the absolute value of -3, but the question said when. So I'm not looking for the speed itself, I'm actually looking for the time, and that occurs at 3 seconds. Letter D, graph the acceleration where it is defined. And again, since the velocity function is made up of a series of segments, I'm not going to graph that this time because the answer is in your packet, but I would find the slope of this segment, and then I would make a horizontal bar on the acceleration graph. Then I would find the slope of this segment and make another bar. Slope of this segment, make a bar. Slope of this segment, make a bar. You've seen several of those already in some other problems. Problem number 3, a particle moves along a vertical coordinate axis. So the particle basically is going up and down a vertical line. It starts with time 0, and they give us a position function. S is measured in centimeters and time is measured in seconds. Find the displacement. Now remember, displacement is change in position. So I'm going to have to find over the first 6 seconds, so that would be S of 6. In other words, where is the particle at 6 seconds? I'm going to go into position function, minus where was the particle initially, and you can see easily by substituting in 0 that the particle was at -4. And you would use your calculator to calculate the position at 6 and go from there. Letter B, average velocity. A, algebra 1. Average velocity is change in position. Think back, it's just simple algebra 1. It's not really a calculus problem. During the first 6 seconds. So we're going to take the value that we calculated in part A, change in position, and then change in time. And whatever that turns out to be, the answer, of course, is in your packet. Centimeters per second, because it's velocity, and up here this would be centimeters. Part C, find the expressions for the velocity and acceleration. Well, they're just asking us to practice the power rule. So to find velocity, it's going to be the first derivative of position, and acceleration is going to be the first derivative of velocity. And again, that will be power rule. Part D, for what values of t, so we're looking for time, is the particle moving downward? Okay, well, if the particle is moving downward, then that means that we're looking for when the velocity is less than 0. So to do this problem, we're going to take the velocity function and set it equal to 0. Then we're going to take whatever times we get and create a little number line. Now, since this is a cubic, the velocity would be quadratic, so I would get 2 times, and I would put time number 1, whatever this turns out to be after I solve it. You can see the answers in the packet, and time number 2. Now then remember, we're going to choose a value out of each region. We talked about you have to know the before and the after. We're going to choose a value in each region and substitute it into the velocity to determine whether the velocity is positive or negative. And wherever the velocity is negative, the particle is moving downward.